All right? Dumb fuzzing. Take a file, flip some bits, see what happens. And we got smart fuzzing. Take a file, understand its internal structure, do all this analysis, fuzz in the structure, reconstruct back. Smart fuzzing is awesome. It does horrible, horrible things, but man, it's a pain in the ass to do. Dumb fuzzing misses a lot of stuff because it's just, well, dumb. We've got to find a midpoint. Well, there's this really interesting tool. And what it does is it finds structure. Instead of having to do it intelligently, it just looks at a random byte stream. And it's called sequitur. Sequitur is a linear time pattern finder. It creates what are known as hierarchical context-free grammars from arbitrary input. And it doesn't slow down based on how much you give it. No, you can give it 100 megs of data. You can take the entire C Windows System32 directory, pipe it in, and it'll be like, oh, well, that's kind of cool. Let me create a structure out of this big amount of noise you're giving me. In short, sequitur is 1000% awesome. But an example of what it's doing. Let's look at the switch statement at the left of this page. Someone bring me water, by the way. We're going to go from switch C, case 1 value equals 2, case 2 value equals 3, case 3 value equals 4. We're going to create a grammar out of that. And that is switch C, A1, B2, A2, B3, A3, B4, with A equaling enter case and B equaling value. This is interesting. We've just extracted meaningful symbols from arbitrary data. Now you might say, oh, but Dan, you know, I can totally do that. I can see that myself. Yeah, you can see that in text. Try that in a random string of bytes. This did it with no user interaction. So let's do a trivial little thing, right? When you compress a file with sequitur, each byte requires, because remember, you know, A could lead to C, C could lead to Q. You know, you have a tree that you have to traverse to recover each byte. You could actually color each byte by how far in the tree you had to go. I don't know how visible it is, but here are 2 examples of syntax highlighting of hex dumps just based on how deep in the tree you had to get. Now, obviously, when you have patterns, and the patterns have patterns, patterns and patterns have patterns, you end up going deep in trees for individual sections. And what do you see? Well, look at this. We've got this blob over here on the right. We've got these repeated sections. We have, oh look, we have structures that just pop out of the data. They just visually show up. Pretty pictures, useful, 2 great tastes that go together great. But can we do more? So I'm creating a tool. Context-free grammars, going to be a fuzzer. I'm calling it the CFG 9000. So the next thing that Craig Neville Manning talks about in his thesis, which by the way is also awesome. Yeah, it is a little funny. I didn't realize he was going to be the chief research scientist at Google, but oh well. So it goes ahead and it turns arbitrary data into the symbol set, right? Great. We can go ahead and draw graphs for how these symbols interact. And we see switch leads to case, case leads to 1, 2, 3, 4, 1, 2, 3, 4 leads to value. Clearly, if we do manipulations on these symbols, we will have much more meaningful manipulation than if we randomly swapped bytes around. I don't care how you randomly swap bytes around. Switch versus SITCH. Oh, I dropped the W. I've really done something meaningful. No, you haven't. Now, if you replace case and value, you might do something meaningful. System might not expect that token in that particular place. So, context-free grammar fuzzer, CFG 9000. Reduce the input data to a stream of symbols, fuzz on the stream of symbols. Shuffle the symbols, drop symbols, repeat symbols. Now, sequitur is not necessarily the best way to generate this stream of symbols. In fact, you know, there's an explicit line of separation between sequitur, a symbol finder, and CFG 9000, which, given a context-free grammar, actually fuzzes that grammar. In fact, sequitur might not even be the right tool set to use. There's a mechanism called suffix trees that the Protos guys are using. Protos, as you may or may not know, destroyed every single SNMP implementation in existence. They're good guys. I'm messing around. But sequitur may scale better. I don't know of anything else that can find patterns in 100 megs of input without caring. Some sample output. Again, I don't have time to do live demos. I threw the source code of sequitur into its own fuzzer. And what do we actually see? Calculate rule usage. P to rule P, to rule P, to rule P, to rule P. Calculate rule usage. Oh, open up calculate rule usage. This is all completely undriven. I just said, go take some symbols and go make some noise and show me some cool patterns. So everything that we can see because it happens to be text, we can also do because it's actually finding the boundaries between a function and what's inside the function. And that's pretty cool. So, things to do. I got to create Requitor, which is a version of Sequitur that's optimized for fuzzer use. I need to generate larger symbols. It's kind of built for compression, and compression doesn't care if it makes a symbol for a 2-byte sequence. However, that's not very useful because 2-byte sequences happen randomly in any data set of normal size. Kiefer Yang in 2001 created an optimization, which is basically if you have 2 symbols that are the same actual literal plaintext, merge them to one. You would think this would be obvious, but it affects some of the performance of Sequitur, so it wasn't in the original version. And you need to do this if you're going to fuzz all instances of a particular trope, a particular set of literals. There's an in-memory grammar requirement. If you are going to fuzz 100 megs of data, you need to have like 800 megs of RAM. There's a variant called Ray that does not have this trait and still keeps linear time. And of course, add the ability to import foreign grammars. I want to be able to interpret a series of files according to the grammar from another series of files. So I can say, hey, this looks like a JPEG. Well, how do I know that? Well, because it's got symbols from JPEGs. Cool. So Sequitur is really cool. It's unfortunately not where we need it. It's not necessarily where I even hoped it would be for BlackHat. But syntax hiding for hexdumps, that worked. And we got some fuzzing out of it. Cool. Another approach. Dot plots. So I remember this old paper. I got a hobby. I like music, like actual music analysis. I remember this thing called Visualizing Music and Audio Using Self-Similarity. It's by a guy named Jonathan Foote over at Xerox. And this is a total brute force solution to analysis. You take a file, you turn it into little segments of time, and you compare each segment of time to each other segment of time. And if they sound the same, you make it white, and if they sound different, you make it black. And there's a tool out there called Disassociated Audio that'll do this if you're also into audio. Well, what kind of pictures do we get? You get pretty cool pictures. You actually have each individual section. This is Day Tripper from the Beatles. And you actually get each individual section from the bridge to the verses. That's where all these little color sections are. They look substantially different. Can we get this out of targets of data that we might fuzz? Anyone actually see Pirate Baby Can Banna Fight 2006? Yeah. Awesome. Pirate Baby MPEG says yes. We can absolutely find fuzzable patterns in a huge number of data sets. Hey, if we can do this to audio, we sure as hell can do this with some set of bits on a hard drive that got compiled by some tool. So what exactly are we doing? Well, Jonathan Hellman's dot plot patterns, a literal look at pattern languages, offers an introduction. So take to be or not to be. Down the center, 2 is a 2, B is B, or is or, not is not, etc. So no matter what, we're getting a diagonal line, right? But look, that 2B in the upper right corner, 2B gets repeated between the beginning and the end. So we get these extra dots along the side. That shows a repeat, right? Now we need to do this instead. If we're going to do this to files, I don't want to use individual bits, although Hellman actually does in his paper. I want to use sections, and I need to figure out if the sections are similar. Remember how I had this similarity metric sitting around from when I found the difference between all the names? We can totally use that to find similarity between, say, 32-byte chunks of a file, and it'll work great. So what do we see for various data sets? Oh, actually, I got to do a little bit of history. The bioinformatics guys, who are the only people who deal with legacy code issues uglier than ours, they go ahead and they use this stuff. But no one, as far as I can tell, has used it to guide security research. Well, what would we want? First of all, we'd want to get a global view of section boundaries. Can I separate out clearly different sections? Secondly, I want a local view of what exactly is going on. Given a certain pattern, can I make some degree of conclusion over visually what's showing up? Java class files, .NET assemblies, CNN's homepage. Oh, we've gone to HTML, which has redundancy on a much tighter scale. And interestingly enough, we see that in the data set. Is that at all visible? I hope it is. SMB torture traffic. We can throw packets into this. Packets being much smaller units of data, packets have their redundancy and differences at much higher frequency. Kernel32.dll. Now, the one thing to notice is that we're actually able to uniquely identify individual sections in this file. We've got this block here, this block here, this block here. Here's one, here's one. Here's a couple of small ones. Here's a large block that has internal small blocks. The idea behind this process on the global scale really works well. Like, for example, human chromosomes, in case you feel like hacking other viruses. The Legend of Zelda. Does anyone here actually know 6502 code? No. But can you identify individual unique sections a hell of a lot better than you can with OD-X? Yes, absolutely you can. Unique section, unique section, unique section. Everything here that creates a grid pattern, and no, the shirt wasn't accidental. Everything here that makes the grid pattern goes ahead and represents another deviation in the file. So I'm releasing a tool shortly. It does autocorrelation, so I'm calling it hardcore, that calculates these images. It's pretty cool. It's really fast because I ported it to C. Nothing says 80 times speed improvement like porting to C. You end up hacking IMAX style because you end up with all these images that are like 10,000 by 10,000 pixels. It's kind of cool to know, man, I need a better view of this. I'm going down to the IMAX theater. The global goal is totally achieved. Fuzzing is a combinatorial game. If you can split the combinations from multiplicative to additive and split out each section individually, you are ahead of the game. You can say, I'm going to do this block, this block, this block, and even if you dumb fuzz that block, and that block, you've at least separated out the problem. Cool. Well, can we get any local knowledge? Is it at all meaningful what particular visual patterns show up? Well, from the original paper written on the topic, we actually can get some documentation of what's going on. So, for example, if you have a series of A's and then a series of B's, you will get two squares along a diagonal. If you get a repeat, ABCD, ABCD, you will get just straight diagonal lines, just like we had with 2B or not 2B. If you get two blocks that look like they've kind of interacted and there's kind of some shuffling going, you get both diagonals and squares, then you have two types of data that have been shuffled in. Now, because we're looking at blocks that have potentially multiple things, you might have two different sub-message types inside of your analysis window. You'll get light crosses, broken diagonals. I encourage you to actually get that paper. It explains a heck of a lot of what you're looking at. But it also doesn't, because there's some weird stuff inside of symbols. It's the mark of a good tool if it shows you weirder things than you can possibly imagine it would have originally given you. You get these lines that have fade outs. You get blocks that look like artwork. You get very highly detailed stuff. And then over here, we get like squares, like fairly large size squares. What's going on? I don't have a freaking clue. I don't have any idea what's going on there. What the hell? And that is awesome. Because I sure as heck didn't know that anything was going on when I did OD-X, but I didn't even know I didn't know what was going on. I just figured it was like random noise. This gives me clear separation. If it's random noise, you get a big gray blob. Now, what's actually kind of interesting is if you have random noise with a little bit of a bias, a little bit of sections, you'll get gray with slightly less gray. Now, whether a computer can see it is another question. Whether your occipital lobe can see it, oh yeah. Yeah, I got me a third of my brain dedicated to vision, and believe you me, I'm willing to use it. So, what do we got to do here? We got to figure out what the heck all these things visually mean. We've got to create some interactive tools for dot plot evaluation. Hey, we can call the field data microscopy. Color.